What if everything you've ever believed about the size of the universe is not just incomplete but fundamentally wrong? Think about it for a second. If someone asked you, how big is the universe? You'd probably answer with confidence. You've heard it before. The observable universe is about 93 billion light years across. That's the number. That's the accepted answer. But here's the problem. It isn't actually the size of the universe, not even close. That number is something far more subtle. It's a carefully constructed idea, a simplified version of reality that scientists often present because the truth is much harder to grasp. The real answer is not just complicated, it's deeply unsettling. Because when you truly examine it, the concept of size itself begins to fall apart. Not slowly, but completely. I want you to follow this carefully, because by the time we reach the end, the way you see the space around you, this room, your body, everything will feel different. Let's start with what feels familiar. We look into the sky with powerful telescopes. We detect the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing that signal, scientists estimate how far that light has traveled. The result? Roughly 46 billion light years in every direction. Double that, and you get the famous 93 billion light years. Seems solid, right? Except it creates an immediate contradiction. The universe is about 13.8 billion years old. So how can something that's only existed for 13.8 billion years appear to be 93 billion light years wide? Nothing can travel faster than light, so how did the edges get that far away? This is where most explanations stop being intuitive and where the real story begins. The answer is not that galaxies are racing through space at impossible speeds. Instead, space itself is expanding. Not objects moving within space, but space stretching between objects. Every moment, new space is being created between galaxies. The distances aren't increasing because things are moving away in the traditional sense. The distances are growing because the fabric of the universe itself is stretching. And here's the part that changes everything. This expansion is not limited by the speed of light. The speed of light restricts how fast things can move through space, but it does not restrict how fast space itself can expand. There is no universal speed limit on the growth of space. Right now, at this very moment, there are galaxies so distant that the space between us and them is expanding faster than light. Their light will never reach us. Not because it's too faint, not because our instruments are too weak, but because it physically cannot cross the ever-growing distance. Those galaxies still exist. They are real, but they are permanently cut off from us. Think about what that means. The 93 billion light years you've heard about is not the size of the universe. It's the size of the region we can observe, the portion of reality whose light has had enough time to reach us since the beginning. Beyond that boundary lies something, possibly much more, maybe infinitely more, and we may never know. Because the expansion of the universe isn't slowing down, it's accelerating. Every second, more galaxies slip beyond what we call the cosmic horizon. Once they cross it, they're gone forever. No signal, no information, no trace will ever reach us again. And this leads to something deeply counterintuitive. The observable universe, in terms of what we can ever interact with, is actually shrinking. Read that again carefully. Even though space is expanding, the portion of the universe accessible to us is getting smaller. Galaxies that were once theoretically observable are being pulled away faster and faster. It's like watching lights in the distance slowly fade out, one by one, never to return. You might think this is just a technological limitation. Build a better telescope, see farther. But this is not a problem of engineering. It's built into the structure of reality itself. No advancement, no future discovery can allow us to see beyond that horizon, because the light from those regions will simply never arrive. So when someone tells you the universe has a size, what they're really giving you is something else entirely. They're describing the boundary of our knowledge, the edge of what we can observe. Beyond that, we are completely blind. We are living inside a cosmic bubble. And that bubble is not expanding in the way you think. It's slowly closing in. And this is only the beginning of the problem. Because once you start questioning the size of the universe, you are forced to confront something even more disturbing. What does distance even mean? It sounds like a simple question, almost too simple to matter. In everyday life, distance feels obvious. You measure it with a ruler, a tape, or even just by walking from one point to another. It's fixed, reliable, objective. 2 points exist, and the space between them has a definite length. That's how we experience reality. That's how we build everything from houses to highways. But the moment you try to apply that same idea to the universe as a whole, it stops working. Because you cannot stretch a ruler from Earth to a distant galaxy. So when scientists say a galaxy is, for example, 10 billion light years away, what are they actually saying? They're not measuring a fixed distance sitting there in space. Instead, they're describing a process. They're saying that light from that galaxy has been traveling for 10 billion years, and based on how space has expanded during that time, they calculate where that galaxy should be right now. But here's the problem that most people never notice. Right now does not mean the same thing everywhere. This is one of the most important insights from Einstein's relativity. There is no universal clock ticking the same way for everyone across the universe. Observers moving at different speeds or existing in different gravitational conditions do not agree on what events are happening at the same moment. So when we say that galaxy is 10 billion light years away right now, we are quietly making a choice. We are choosing a specific frame of reference, a specific way of slicing space and time, and calling that version of now the correct one. But it's not the only one. In another valid frame of reference, that same galaxy could be at a completely different distance at that same moment, because that moment itself is defined differently. So which measurement is correct? The uncomfortable answer is all of them and none of them. Distance, at cosmic scales, is not a fixed property of reality. It is something that depends on how you choose to observe and measure the universe. It depends on your coordinate system, your motion, your assumptions. It is not absolute. And that tells us something profound. Space does not come with a built-in ruler. When cosmologists measure distances, they often use what are called comoving coordinates. This is a framework where the expansion of the universe is factored out in a specific way, allowing galaxies to be treated as if they are at rest relative to the expanding fabric of space. It's a useful system. It makes calculations manageable, but it's still a choice. Another observer, somewhere else in the universe, moving differently through space-time, could use a completely different system and measure entirely different distances, and neither of you would be wrong. This is not just a technical detail buried in equations. It changes the meaning of size itself, because if distance depends on the observer, then size, which is built from distance, cannot be an intrinsic property of the universe. It becomes something relational, something defined by perspective. Now let's go deeper, because this idea doesn't stop at measurement. It goes into the very structure of reality. In general relativity, the theory that describes gravity and the large-scale behavior of the universe, space and time, are woven together into a single entity, space-time. And the way distances and durations are measured within this structure is determined by something called the metric. You can think of the metric as the rule book for geometry. It tells you how to calculate the distance between nearby points, how time flows, how paths curve. It is, in a sense, the DNA of space-time itself. But here's the crucial detail. The metric is not fixed. It evolves. According to Einstein's field equations, the metric responds dynamically to the presence of matter and energy. As the universe changes, so does the very definition of distance. The geometry of space-time is not static, it is alive, constantly shifting. So when we say the universe is expanding, we're not just saying that objects are moving apart. We're saying that the metric itself, the underlying structure that defines distance, is changing over time. Distance is not just something you measure. It's something that evolves. To make this more intuitive, imagine you're standing on the surface of a balloon, not outside it, but on the surface itself, like an ant. Now imagine that balloon slowly inflating. You and another ant are not walking, not moving at all relative to the surface, but the distance between you keeps increasing. Why? Because the surface itself is stretching. Now, you could try to measure that distance at different moments. At one point it's shorter, later it's longer, so what is the true distance between you? There isn't a single answer. It depends on when you measure it. The universe behaves in a similar way, but with an important difference. The balloon exists in a higher dimensional space. You can step outside it and measure it from the outside. You can define its size from an external perspective, but the universe doesn't give you that option. There is no outside. There is no higher vantage point from which you can observe the entire universe and assign it a definitive size. The universe is not sitting inside something larger that you can step back into. It is everything that exists. So asking how big is the universe is like asking how big is everything. There's nothing to compare it to. And without comparison, size loses its meaning. This is a point that is easy to hear but difficult to truly absorb. Size is always relative. A mountain is large compared to a human. A galaxy is large compared to a star. But the universe as a whole, what is it large compared to? There is no answer, because there is nothing else. The universe is the reference, and a reference cannot measure itself in any absolute way. And just when it feels like this idea has stretched your intuition far enough, physics takes it even further into a phase of reality where the concept of size doesn't just become unclear. It becomes almost meaningless, because to understand that, we have to go back to the very beginning, to a moment when the universe didn't just expand, it exploded outward in a way that defies comprehension. To understand just how far this goes, you have to return to the earliest moment we can even begin to describe the birth of the universe itself. Not seconds after the beginning, not even fractions of a second, but an instant so small that it almost escapes the idea of time altogether. Right after the Big Bang, something extraordinary happened. The universe didn't simply expand, it underwent a phase known as cosmic inflation. During this brief moment, space itself expanded at an exponential rate, far faster than anything we see today. Not a steady growth, not a gradual stretching, but a sudden and violent swelling of reality itself. In less than a trillionth of a second, the universe grew by an unimaginable factor. Numbers like 10 to the power of 26 are often used to describe this expansion, but even that doesn't capture how extreme it could have been. Some theoretical models suggest expansions so large that writing them down becomes almost meaningless numbers stacked on top of numbers, beyond anything the human mind can visualize. Now pause and think about that. Before inflation, the universe may have been smaller than a single particle. After inflation, it was already vast beyond comprehension. And since then, for 13.8 billion years, it has continued to expand, first slowing down, and now accelerating again. So when you hear that the observable universe is 93 billion light years across, you're not hearing about the full universe. You're hearing about a tiny fraction of it, a visible patch, a small window into something that could be incomprehensibly larger. It could be thousands of times bigger, million, or it could be infinite. And here's the unsettling part, we may never know which one is true. Because inflation doesn't just explain the size of the universe. In many of its strongest versions, it never truly ends. This idea is known as eternal inflation. According to it, while inflation stopped in our region, allowing galaxies, stars, and eventually us to form it, continues elsewhere, constantly, endlessly, creating new regions of space-time over and over again. Each of these regions can become its own universe, with its own physical laws, its own constants, its own structure. This is what leads to the concept of the multiverse not as science fiction, but as a serious consequence of modern cosmology. In this picture, what we call our universe is just one bubble in an endless cosmic foam. And each bubble might be enormous on its own. Now ask yourself again, what is the size of the universe? Which one are you measuring? Earth? The entire multiverse? Or something even beyond that? At this point, the question itself starts to break down. Because even if the universe is not infinite, even if it is technically finite, it still may not have a clear, fixed size. Imagine a universe that is curved, like the surface of a sphere, but in 3 dimensions. In such a universe, you could travel in a straight line forever and eventually return to your starting point. There would be no edges, no boundaries, no walls. It would be finite, but unbounded. You could measure its circumference in a sense, but that number would depend on when you measure it, because the universe is expanding. It would also depend on your frame of reference, because distance itself depends on how you define simultaneity. So even in a finite universe, size is not a single stable number. It's something that changes over time, something that depends on perspective, something that cannot be pinned down in any absolute way. And remember, from inside that universe, you can never step outside to see the whole picture. You are always limited to your observable region, always confined within your cosmic horizon. So even if the universe has a well-defined total size in some abstract sense, it is practically impossible to measure it completely. Now bring this back to something more immediate. Look around you. The room you're sitting in feels solid. The walls feel fixed. The space feels measurable. You could take a tape measure and determine its length, its width, its height. Everything seems stable, reliable, real. But even here, the idea of size is not as fundamental as it appears. What determines the size of your body? At the deepest level, it comes down to atoms. The spacing between atoms defines the structure of matter. But what determines that spacing? It's governed by electromagnetic forces, the interactions between charged particles, the balance between attraction and repulsion at the quantum level. If those forces were slightly different, atoms would be larger or smaller. And if atoms were different, everything built from them would change. You would be a different size. The room would be a different size. The entire scale of reality would shift. So the size of things, even at the level you experience every day, is not fixed in any absolute sense. It depends on the values of fundamental constants, the charge of the electron, the mass of particles, Planck's constant. Change those, and you change the size of everything. Now here's the deeper question. Why do those constants have the values they do? We don't know. In some theoretical frameworks, like string theory, there could be an enormous number of possible configurations, each with different constants, different physical laws, different structures of reality. In many of those possibilities, atoms wouldn't even exist. And in those where they do, their sizes could be radically different. So the size of everything you see, the scale of your world, your body, even the observable universe is not something fundamental. It's the result of a particular set of conditions, a kind of cosmic accident. And in a different universe, size itself might mean something entirely different or nothing at all. But this still isn't the deepest layer, because modern physics suggests something even more radical. That space itself and everything we measure within it might not be fundamental at all. And to understand that, we have to step into one of the most surprising ideas ever developed in theoretical physics. An idea that suggests reality, as you experience it, might be more like a projection than a place. This is where physics takes a turn that feels almost impossible to accept at first. Because up until now, even as concepts became unstable, one assumption still remained in the background: that space is real, that it exists as a stage where everything happens. That distance, even if complicated, is still ultimately part of the foundation. But what if it isn't? What if space itself is not fundamental? This is exactly what the holographic principle proposes. It's one of the most profound insights to come out of the study of black holes and quantum gravity. And it tells us something that sounds almost absurd at first: that everything happening inside a volume of space can be fully described by information encoded on its boundary, not inside, on the surface. Imagine that for a moment. A three-dimensional region, with all its depth and structure, completely described by a two-dimensional layer that surrounds it. Like a hologram, where a flat surface contains all the information needed to produce a full three-dimensional image. Except this isn't just an analogy. In certain well-understood models of physics, this is mathematically exact. One of the most studied examples is known as the ADS-CFT correspondence. It shows that a theory of gravity in a higher dimensional space can be completely equivalent to a quantum field theory without gravity on its lower dimensional boundary. Two descriptions, different dimensions, same physics. That alone is already extraordinary. But now think about what it implies. If the three-dimensional bulk space is equivalent to a two-dimensional description, then the extra dimension, the depth we experience, is not fundamental. It emerges from something more basic. In fact, in these models, what we perceive as distance in the third dimension is directly related to patterns of quantum entanglement in the lower dimensional theory. Let that sink in. Distance is not built into reality. It is constructed. It arises from relationships within a deeper quantum system. Change those relationships, and the geometry of space changes with them. Stretch the entanglement structure, and distances expand. Rearrange it, and space itself reshapes. So when you ask how big something is, you are asking about a property that may not even exist at the most fundamental level. You are asking about the shape of something that emerges from something else entirely. And that leads to a possibility that is as unsettling as it is fascinating. At the deepest level of reality, there may be no space at all, no distance, no size, only information, only quantum states interacting in ways that give rise to the illusion of space-time, much like temperature emerges from the motion of particles. Temperature feels real. It can be measured. It affects everything. But it is not a fundamental property. It does not exist at the level of a single particle. Space might be the same, real in experience, useful in physics, but not part of the deepest layer of existence. If that's true, then asking for the size of the universe becomes something like asking for the temperature of a single electron. It sounds like a valid question, but it doesn't apply at that level. It's a mismatch between concept and reality. And this is where everything you've been building up to begins to shift in a very personal way. Because it's one thing to say the universe might not have a size. It's another to realize that even the space around you might not be what you think it is. The room you're sitting in feels stable. It feels like it has dimensions: length, width, height. You can move through it. You can measure it. You can interact with it. All of that is real at your level of experience. But beneath that experience, the structure that creates those dimensions may not include space at all. It may be something far more abstract, something that doesn't resemble distance or direction in any intuitive sense. And yet, from that abstract layer, everything you see emerges. This idea has been gaining strength in modern theoretical physics. More and more, evidence points towards space-time being a kind of emergent phenomenon, something that arises from deeper quantum information structures, rather than something that exists on its own. In this view, the universe is not a vast empty container filled with objects. It is a network, a system of relationships, a structure of information that gives rise to geometry as a secondary effect. And if geometry is secondary, then size is too. Which means the question we started with, how big is the universe, may not just be difficult to answer. It may be fundamentally misguided, because it assumes that size is part of the universe's basic description, But if size only appears at higher levels of reality, then at the deepest level, the universe doesn't have one. Not because it's too large to measure, but because large doesn't apply. Now, this doesn't mean that space is an illusion in the sense that it's fake or meaningless. Just like temperature, it's real in the context where it appears. It has consequences. It can be measured. It governs how things behave. But it is not the final layer. And realizing that creates a strange kind of tension. Because everything in your daily life depends on space being real. Movement, structure, form, everything assumes that distance exists. And yet, at the deepest level we can currently describe, that assumption may not hold. This is what makes modern physics so unsettling. It doesn't just give you new answers. It takes away the questions you thought made sense and replaces them with something far more subtle, something that forces you to rethink what it even means for something to exist. But we're still not done. Because even if you accept all of this, even if you accept that size might be emergent, that space might not be fundamental, there is still one more piece that makes the situation even more strange. Something that is actively shaping the future of the universe right now. Something we can observe, but still don't fully understand. And it's pushing the universe into a state where the idea of size becomes even harder to define. Because the universe is not just expanding, it's accelerating. And that single fact changes everything about how we think of its size, not just philosophically, but physically, in a way we can actually observe. This acceleration is driven by something we call dark energy. It's one of the biggest mysteries in modern physics. We don't know exactly what it is. We don't know where it comes from. But we can measure its effects with remarkable precision. The simplest explanation traces back to Einstein himself, the cosmological constant. A constant energy density that fills space uniformly, not clustered like matter, not localized like radiation. Just there, everywhere, always. And here's where it gets strange. If the energy density of empty space remains constant, then as the universe expands and creates more space, it also creates more dark energy. More space means more energy. More energy drives faster expansion. Faster expansion creates even more space. It's a feedback loop, a self-reinforcing cycle that doesn't slow down, it intensifies. And this leads to a very specific future. As time goes on, galaxies will continue to move away from each other at increasing speeds. Not because they're traveling through space faster, but because the space between them is stretching more rapidly. Eventually, only the galaxies gravitationally bound to us, our local group, will remain visible. Everything else will disappear beyond the cosmic horizon, not gradually fading into darkness, but fundamentally slipping out of causal contact. There will come a time, trillions of years from now, when observers in our region of the universe will look out into the sky and see almost nothing. No distant galaxies, no cosmic microwave background, no evidence of a larger universe, just a cold, empty darkness. From their perspective, the universe will appear small, isolated, finite, and they will have no way of knowing that it was ever anything more. This is one of the most unsettling consequences of accelerated expansion. Not only does it limit what we can observe, it erases evidence over time. It hides the past. It shrinks the accessible universe, even as the total universe continues to grow. So again, we are forced to ask, what does size even mean in a universe like this? If the total universe keeps expanding forever, then its size, if you insist on defining one, is not a fixed number. It's not something you can write down and circle as final. It's a moving target, always increasing, never settling. Yesterday, it was smaller. Today, it's larger. Tomorrow, it will be larger still. And there will never be a moment when it stops. So what exactly are you measuring? A snapshot in time? A temporary state of something that never stabilizes? Even that doesn't fully capture the situation. Because in many of the most accepted models of the early universe, especially those involving eternal inflation, our entire observable universe is just a tiny region within something far greater. A single bubble, and beyond it, more bubbles are constantly forming, each one potentially containing its own universe, with its own laws, its own constants, its own version of reality. This leads to the idea of the multiverse, not as a speculation, but as a natural extension of the equations that describe inflation. In this picture, asking about the size of the universe becomes even more complicated, because now you have to clarify what you mean. Do you mean our observable region, our entire bubble universe, or the full multiverse, containing infinitely many such bubbles? It's like standing inside a single drop of rain and trying to measure the size of the ocean. You can measure the drop, you can analyze its structure, its boundaries, its contents. But the ocean itself, the full extent of what exists, is beyond your reach, beyond your instruments, beyond your ability to even define clearly. And in many versions of eternal inflation, The multiverse is not just large, it is infinite. Not approximately infinite, not just unimaginably big, but truly, mathematically infinite. And if that's the case, then size stops being a meaningful concept altogether. Because infinity is not a number you can compare. It's not something you can measure in the usual sense. It doesn't behave like finite quantities. Now step back and look at where this leaves us. We started with a simple question: how big is the universe? And now we've reached a point where the best possible answers are not numbers but frameworks, not measurements but interpretations. Because depending on how you define the universe, how you define distance, how you define observation, you get completely different answers. And none of them can claim absolute authority. This is not a failure of science. It's a reflection of the depth of reality. Because reality at this level does not conform to our everyday intuitions. It doesn't offer simple, fixed properties that we can easily label and measure. Instead, it presents something far more dynamic, far more relational, and far more subtle. And that brings us to one final step. Because after everything we've explored, cosmic horizons, relativity, inflation, dark energy, the multiverse, and the possibility that space itself is emergent, we are left with a question that is even more fundamental than the one we started with. Not how big is the universe, but is size even a real property of reality at all? Or is it something that only appears at our level of experience while disappearing completely at the deepest level? Because if that's true, then the answer we've been searching for this entire time was never a number to begin with. It only felt like one. Because everything about how we experience reality trains us to think in terms of size. Bigger, smaller, closer, farther. These are the categories we rely on to make sense of the world. They work perfectly at the human scale. You can measure a table, map a city, calculate the distance between planets. In that domain, size feels not just real, but fundamental. But what you've seen step by step is that as you push deeper, far beyond everyday experience, this concept begins to lose its footing. At cosmological scales, size depends on how you define distance, and distance depends on your frame of reference. In an expanding universe, even that definition evolves over time. There is no fixed geometry quietly sitting in the background. The structure itself changes. Then inflation stretches everything beyond comprehension, potentially creating a universe so vast that what we observe is only an infinitesimal fragment. And in eternal inflation, even that fragment becomes just one bubble among infinitely many. Then dark energy takes over, accelerating expansion, isolating regions of the universe from one another, shrinking what is observable even as the total grows without limit. And just when it seems like size might still survive as a large but meaningful concept, the holographic principle and quantum gravity step in and challenge the very foundation, suggesting that space itself is not fundamental, that distance is not built into reality, that what we perceive as geometry may emerge from something far more abstract. At that point, the idea of size doesn't just become uncertain. It becomes optional, something that appears under certain conditions, like temperature or pressure real in context, but not part of the deepest description of existence. And this leads to a possibility that is both unsettling and strangely elegant, that the universe does not have a size. Not because it's too big to measure, not because we lack the tools, but because size may not be the kind of property the universe possesses at its most fundamental level. It's like asking what color the number 7 is. The question feels structured, it uses familiar language, but it doesn't apply to the thing you're describing. And that distinction matters, because it tells you something important not just about the universe, but about the limits of human intuition. We evolved to understand a very narrow slice of reality, a world where objects are stable, distances are fixed, and time flows in a consistent way. That intuition is incredibly useful. It allows us to build, to navigate, to survive. But it is not designed to understand the universe at its deepest level. And physics, over and over again, exposes that gap. It showed us that Earth is not the center of everything, that time is not absolute, that matter is mostly empty space, that particles behave like waves. And now, it's showing us that space itself may not be what we thought it was. Each time, the pattern is the same. What feels obvious turns out to be incomplete. What feels fundamental turns out to be emergent. And what feels like a solid foundation turns out to be just one layer of a much deeper structure. So when you ask, how big is the universe? You are not just asking for a measurement. You are asking whether reality itself is built in a way that allows that question to have a clear answer. And the honest response, the one supported by everything we currently understand, is this. At the level of fundamental physics, it might not. That doesn't mean the universe is mysterious in a vague or unknowable sense. It means it is structured in a way that challenges the categories we use to describe it. It means we are still in the process of discovering what the right questions even are. And that is where things become interesting. Because the absence of a simple answer is not a limitation, it's an invitation. An invitation to rethink what we mean by space, by distance, by reality itself. An invitation to explore deeper layers of understanding where the familiar concepts dissolve and new ones take their place. After decades of study, one thing becomes clear. Every time we think we've reached the bottom, every time we believe we've found the fundamental layer, something else appears beneath it. Another structure, another explanation, another shift in perspective. The universe does not resist understanding, but it does refuse to be simple. And maybe that's the most important takeaway of all. Not that the universe is big, not that it's infinite, but that the question of its size leads us to something far more profound. It leads us to the realization that reality is not built the way we instinctively imagine it, that the concepts we trust the most, space, distance, size, may only exist at the surface. And beneath that surface lies something deeper, something we are only beginning to understand. So the next time you look around the room you're in, notice how solid everything feels. Notice how clear the distances seem, the walls, the space between objects, the sense of scale, it all feels certain. But now you know something most people don't. That this certainty may not extend all the way down. That what you're experiencing could be a layer real, consistent, reliable, but not fundamental. And that beyond it, the universe may not have a size at all. Not because it's beyond measurement, but because, at its deepest level, there may be nothing there to measure.